have a so good weapon and I have jump one. No, that is not how it works. No. Bad Joe. Bad Joe. Bad
Hi, John Ford. Oh, and hi, Maisha. Yeah, I don't know. To be honest, I think John has been here for a while, but I'm not saying that. But hello, Maisha and John Ford. And wait, okay, let me do this officially. I'm going to stay out of that melee. You can go to, what do you call it? Not IHOP. What's the other one? Denny's, and you can work that out in the Denny's parking lot. But let me, oh my God, it's already rough. It's already this class, but let me do my part. Okay. Hi, John Ford. Hi, Maisha. And also, hi, Maisha. Hi, John Ford. Good afternoon, Andrew. Hello, Nick. Good afternoon, Zeman. Oh, sorry. Wait, confusion. Actually, wait, I'm sorry. I think, okay, there might be something. All right. Anyway, good afternoon, Andrew. Hello, Nick. Good afternoon, Zeman. Good afternoon, Manoj. Good afternoon, Catherine. Good afternoon, Athea. Good, hello, Nick. Yes, mine too. Okay. Okay, that's funny, John. Okay, that's funny, Maisha. I'm gonna keep going. Alan, someone's here. Pardon me for a second. Okay, back. So confusing. Okay. Okay, I'm going to skip the John Maisha thing. We'll deal with that on divorce court at 4:30 p.m. Good afternoon, Lisa. Good afternoon, Alyssa. Good afternoon, Jaylyn. Also, hello, Nick. Good afternoon, Jessica. Hello, Ilona. Good afternoon, Wisha. Yeah, long time no see. Why is that? But that's true. Oh, yes. Good afternoon. Yes, quite right. Thank you for acknowledging. Okay, I'm going to skip that. Yeah. Oh my God, that's funny, Nick. All right, I'm going to skip that because there's children near me. But yes, Denny's okay. Got a streak on you. I feel like the Undertaker. I'm not sure you mean Undertaker. You might mean underdog, John. Undertaker's in, well, anyway. Thank you. Yes, better. Thank you, Mark. I appreciate it. And the reason I wasn't here last Wednesday was because of that whole 102 business. I hope you guys saw the video. We'll talk about that. Okay. I'm skipping. Oh my God, that's funny, Maisha. Okay. Oh, I will see Maisha's challenge and I will raise it 8 in the morning, Physics 204 next semester, be there or be a right angle rhombus challenge. And I'm not even kidding. Okay. But all right. I mean, literally, but I hope to see you all in 204 at whatever time. But yes, there will be an 8 in the morning section. And yes, it'll be in real person. And all right, anyway. Okay. Good afternoon, Lizzie. Hi, Leslie. Emoticon John. Hello, Rachel. Oh my God, that's funny. Okay, hi, Michaela. Oh, you do mean the Undertaker. Okay, you mean the Undertaker. I believe you. I believe you. As long as it was a mindful, conscious decision. Okay, I'm skipping this stuff. I'm trying to get to physics. Okay, hilarious. I know you didn't say anything about 8 a.m. I'm saying 8 a.m. Like, that's a true story. You guys can look it up. If you want to have physics not online and you want to have physics with looks like me, which I would recommend against, then you're going to be meeting me at 8 in the morning in the physics lab at 59th Street. And I wish I were joking. But anyway, okay. We are going to start. We're going to start. Wow.
I'll wait for Gigi.
Thank you, Rachel. Yes, it does, even to me. I know. But at least no one, well, anyway. Okay. Thank you, private chat person. Got it. I appreciate it. Got it. Yeah, no, and I'm sorry. No, and me too. And I'm blah, 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 blah. That was just all gratuitous on my part. Let's do some physics here. Yes, that is actually funny. So is that. Okay, wait, one thing, just to be clear, we are going to do some physics here, believe it or not. I tried it once. It didn't hurt that bad. But one thing too, the good news is I feel like finally we got over that hump. And I think most of you have I think people have their midterms back. I will admit, someone reminded me in a text, which I totally appreciate, a couple minutes before class. I did invite you to text me if you had any issue, couldn't find your grade, had an issue with your grade, blah, blah, blah. And I had forgotten, it is true that, and please take this in the way that I mean it. If for whatever reason you did hand in your exam late, and to anybody that applies, it was with permission and it was with prior arrangement with me and all of that. But if you did hand in your exam late, then that may mean that you have not gotten your exam grade back. This is not a punishment. It's not a consequence. It is literally a consequence of just that I fell so far behind that I prioritized in the way that I did. So if you're still waiting on a grade, that I believe is because your document came in later than the others, or went through some iterations or some technological problems or something. And so yours is still coming, and that's just the way it is. Thank you. Okay, no problem. So again, so if you're waiting, that's the reason, and that's just a sequencing reason. But good. No, I'm totally psyched. And then, yeah, no, and to all of you, although this is not the time right now, for sure, if you have any issue with anything in the exam, just wanting to know how to do something better, or you couldn't read my handwriting, or you want to politely question some point deduction somewhere, I'm open to all of that. The best way, honestly, is not right at this moment, but later on, to text me and ask for like a 15-minute phone call or whatever. Just text me or email me, but text me, and just as long as you present it as a polite question, like I would like to look into this with you, then we will discuss, and there's no statute of limitations. As long as we discuss it before the final grades are due, then it'll be fine. And that includes if you're concerned about why I took off points where I did. Just as long as you come to me in peace, I will meet you in peace, and we'll resolve it. Just not today, to be honest, but just text me and we'll set up an appointment. Now on that, but thank you for the thanks and for your patience. On that, you will notice, I believe, I hope, that in your Google Classroom a couple hours ago, I did put in a document that is meant to help you practice for the final exam. First of all, can you confirm or deny, do you guys see that in the, it's under exams, and it's, yes, great. All right, awesome. We're gonna start talking about that. Great, I'm glad you have it. I would, from here on in, all we care about is that document. That's a document you should be worried about when you're doing physics outside of class. That's a document you should have with you when we're doing physics in class. Let me back up also and say, if you still wanted to, could you hand in old things before classes end next Monday? Yes, you can. As long as a link is up, you can use the link. Will I sometimes maybe not give all the points if something is late enough? Maybe, but certainly if you want to, you can still hand in old things. However, my recommendation to everybody is, if you're going to, whatever time you have outside of class to spend on physics. Yeah, I'm getting to, good question, John. I'm getting to that right now. Fair question. Let me just say though, to try to sort of go, and everything I'm saying right here, I will try to put explicitly in Google Classroom, but from here on in, what you want to focus on outside of class time is the practice exam document for the final exam. That's what we're going to be dealing with in class from here on in. When is the final exam? Okay, it says tentatively in Google Classroom, it says that on approximately Tuesday, today's the 7th. Wait, I keep getting this wrong. Today is the 6th. On approximately Tuesday the 14th, whatever that Tuesday is, a week from tomorrow, approximately, I will post the final exam that night at approximately 8 p.m. You will have until approximately the following Monday, which is that right? Wait, I keep getting this wrong. Yes, I believe the following Monday you'll have to do it on your own time, do it at home, do it within open universe. So it'll be posted essentially the day after the last day of classes, and it'll be due back essentially the end of the final exam, or toward the end of the final exam period. This is written in Google Classroom. I'm saying approximate on all these facts right now because I still reserve the right to fine tune this, to talk with Professor Walters, to talk to other Professor Walters, and make sure this is all exact. When it's all exact, I will put final confirmation in Google Classroom. But basically what you should assume is that the day after classes end, I'll post a final exam, and more or less toward the end of the final exam period, that exam will be due back to me. You should assume same rules and same procedures as the midterm, and you should assume that the final exam will look very, very much like the thing that I just put in Google Classroom this morning. Even that is an approximate rough draft. I will make updates and changes to that as we get closer. Any update or change I make will just make it that much more similar to your actual thing. Okay, so just like with the midterm, we're trying to minimize surprise here and maximize excellent performance. You'll also notice that in the practice, so you can open up the practice document now. It might look somewhat familiar. It might look somewhat intimidating. All we're going to talk about from here to the end is stuff to help you with that practice document. You should also note that in the practice, you could also note that in the practice document, there are solutions like right in there right now. So for some of you, that'll make it easier to practice. For some of you, it'll make it more distracting. Like you might want to, but they're there. Basically the final exam, and hopefully the final exam won't even be quite as long as what that document is. The final exam doesn't have a lot of material on it. It's only explicitly about what we've done since the midterm. Your ability to understand it and navigate it will be that much better, if you have learned all the material prior to the midterm. But explicitly, it's only about the bits that we've done since then. What the final exam really is about, and this is what we're going to get into today, really, it's an exploration from more than one perspective of the whole kind of inclined plane that you were asked to study in Lab 5. Okay, it really is kind of like a couple of different perspectives, views, understandings, approaches to the rough inclined plane that was your activity in Lab 5. Now, I've said some things to help you with that. Like last week, we talked about friction sort of in detail, but there's some things that I haven't said explicitly about that inclined plane, such as I haven't really explicitly showed you what to do with the fact that it is inclined. I haven't really discussed angles and what to do with them yet. That's what's going to happen for today and for the rest of whatever time we have together. I'm going to stop for a second and look in the chat. But basically what I'm saying is this: anything that I say from here on until the end is meant to help you solve the final exam, which will look like that document. There are some things I'll say which are explicitly on the page of that document. Like you'll see at a certain point, I will literally be answering questions that you have about it. For example, next class. Once you've had a chance to look at it and you come and you bring questions to class, I'll explicitly address things that are in that document. Today, I'm going to back up and do a problem that won't at first. I'm going to do a problem that is meant to help with angles and vector components and all of that. It is meant to be the last step up we need to climb in order to fully understand the inclined plane. So it won't, when I get going in a second, what we're going to do, I think, is explicitly necessary and helpful for that document. It won't look that way at first. The problem that we're about to do, you should just do with me and take notes and blah, 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 blah. And then when we're done with it, you will see how to transfer it to the inclined plane and to that exam document that I put there. So I'm sort of going to ask you to bear with me for a little bit, for we're doing one more problem together, but it is absolutely the underpinnings of that final exam document. I'm going to pause for a second, just going to look for the chat, see if this is clear. Hold on. Okay. So again, to answer John Ford's question, the final basically will be posted next Tuesday and will be basically due back the following Monday. You'll have a week to do it. Okay. Yeah, okay. You'll have a week to do it. Same deal as before. You take it home, you do it in your own time, you help each other, you use this practice document. The actual final document will look very much like this, blah, 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 blah. Okay. So from here on in, I want to try to do the material with you of the practice document. Okay, cool. Okay. So let me just switch. Okay. So quick question. So again, what I'm about to do is do like a final practice problem with you that I think will help. Also, it's understood that, that everything I'm saying, like in some ways you've already seen in lab, but it was probably confusing in lab. In some places you learn certain things in lab, and other places you probably just had to accept things on faith and sort of like grunt your way through it. So I'm here trying to put those things together. At a certain moment, if you ever have the reaction like, oh, well, that makes sense now, I wish I'd understood that when we were in the middle of lab, then I totally sympathize and I totally hear you. But please remember, if you have that reaction, that means that something has just got clicked into place. And that means that what it might feel like it was too late for lab, what it really means is that both lab and we have done our job to click it into place for you before you have to do it on the final exam. And that's what this is really about. So I'm going to pause for a second and just say, in fact, I'm going to, yeah, okay. So what we're going to do today, and I'm going to pause to make sure you're with me, but what I'm about to embark on is, in general, how to apply Newton's second law to a two-dimensional set of forces. Like you've looked at some system schemas, you sort of keep kind of looking at free body diagrams with me, but we never go that deep into them. You had this big, complicated two-dimensional problem in lab that involved an inclined plane, it involved friction, involved all these elements. We've never really looked at the two-dimensional, the angled aspect of it. So that's what we're here to do. Therefore, what I'm gonna present to you right now is a box, as it says here on the sheet. This is gonna be a box on a rough horizontal surface being pulled at an angle. So this itself is, if you like, an inclined plane angled at 0. Like this plane, we're looking at kind of like what you did in lab 5 again. We're looking at an object on a surface, but the surface here is flat, and yet I'm going to pull the surface at an angle. So it's like a box on the floor that I'm trying to yank across the floor with some kind of rope that's angled. And let me rush to make clear, if I succeed in pulling this block across the floor, then I will succeed in literally just that, pulling it across the floor. If I succeed, the box will accelerate horizontally, even though I'm pulling it at an angle. Why am I pulling it at an angle? Because I'm a human being who doesn't want to crouch down on the floor next to this thing. Like I'm pulling an angle just for the idea of leverage and practicality. I'm pulling the rope at an angle like you often would, or as though you were pulling a sled or something like that. But if all things work out properly, the box will accelerate horizontally across the floor. What our ultimate question that we're going to solve here, and it will take us more than today. Okay, I got to warn you of that too. Our ultimate question is like, how fast is this block going to accelerate? But in order to get to that point, we have to do all the diagrams and all the force components and all that stuff just in the same way you did or do have to do with an inclined plane like lab 3, so lab 5. This is a way for us to look at how angles work before putting them in before the whole plane itself is angled. So this is going to be the situation. Block of mass M on plane with roughness. So the roughness has two coefficients of friction, one for static friction and one for kinetic friction. And I'm pulling the block with a rope that has tension in it, tension designated with capital T, and I'm pulling the rope at an angle theta. So that's the setup. To the left, I'm giving you the values for each one of those terms. And I'm trying to do it this way so that you can see in general how you solve a problem like this, even though I happen to give you the numbers that apply to this specific situation. We're going to start in a second solving it, but two quick things just occurred to me. One, I want to check in the chat to make sure you're with me, but two, also, for good or for bad, this does assume, I want to get to the end of the material with all you guys and have it as clear as possible for the final exam. I am assuming that at some point you will have watched those videos that I had to post instead of class, whether it's sometimes with this section, I have to post the morning class video and then you watch that instead of class. Bummer, but part of asynchronous learning. The other Monday I had to miss, so I post 3 other videos. Please remember that anytime you watch any of those videos and you even just send me in good faith the slightest indication that you did that, you get points for that. But also, oh, okay, cool. Oh, cool. Okay, no, and I believe you. No, I'm glad. I'm just trying to remind everybody that it's not too late to watch those videos. And the more you watch them, I think the more all this will make more sense. But cool, it sounds like 2 people. Oh, cool. Oh, no, oh, okay. Now, this is a good question. Wait, fair question. Okay, no, and thank you. This also proves you're totally paying attention to me. Okay. Huh. Okay, by the way, the other class is not as funny as you. I know that's true, but then sometimes they have to watch these videos. So yeah, I know the other class is not as funny as you. Okay. But now, fair question of Rachel's and Starnisha's. Wait. I did, but only got points for one, so I stopped. Oh, wait. Okay, well, hold on. First and foremost, the main thing is just watching the videos will make your life a lot easier, like to take this final and all of that. But it is true that for sometimes, like in those, and it's not too late for what I'm about to say. When I posted those things like we don't have class today, when I post like urgent, no lecture today, but you get points for watching these videos or whatever, I'm just saying, like all of you, you responded to those urgent things. And I think we're pretty caught up with this. Like when I just send like urgent, just so you know, there's no class today, please reply yes in the window. So you get like 8 points automatically or whatever it is each time for saying yes. But I'm just saying here now, and it's not too late. For those times, in the recent couple of times where I actually put in videos in that thing, and said, like just go back and check. The last couple of times I actually said, you get points for each video you watch. I think, in other words, last Monday there was 3 videos and I said you get like 7 points for each video you watch or something. And then last Wednesday there was 1 video and I think I said you get like 16 points or something for watching video. All I'm saying is if you've actually watched the video, go back to that portal. I'm not talking about commenting on YouTube or anything like I love that when you do that. That's totally awesome, but I can't make you do that. I'm saying in the portal for our class, and I wouldn't make you do that, but in the portal for our class, any of these videos that you actually watched, even though yes, technically they're required, but like just because I want you to do the good thing and be rewarded for it. Any of those videos that you watched, go back to the portal, the urgent no class today portal, and you can even screenshot a part of the video or just write out a sentence like you usually do for game assignments and just say like, I watched video 2 about mass and weight, like the part where you said weight is mg helped me. Just like give me a sentence, just indicating something you got out of it. You're not proving anything. You're just telling me in good faith that you did it, and I'm giving you the points in good faith. You lie and get away with it? I'm sure you could, but I don't want to get into all that. I'm just saying most people, if they would even take the extra effort to write, you know what I'm saying? You don't have to prove it. Just take the 2 minutes just to tell me you watched the video. And I'll believe you. And if you screenshot or something, or you give me a quick example of something you got out of it, that'll make me feel good. But I'm just saying you'll get extra points in those portals to indicate that you watched the videos. That's all. Sorry. So you don't have to prove it. Just tell me. Wait, okay. Sorry. Oh no, yeah. Sorry. No, sometimes I do, but sometimes I don't. Wait. No, and this is the thing. Okay, and I want to get to the material here, and I don't want to. Wait. Yeah, no, I'm just saying, if you watch the videos, I'm not saying you have to do anything in YouTube. I'm not saying that. Like, that would be like weird. I'm saying literally in the assignment portal in these assignment portals, when I miss class and I post the video instead of class, just in that portal, just respond to me and just say like, I watched the video. And if you watched all 3 and you're telling me the truth, and you say I watched all 3, I'll give you the points for all 3. It's not meant to be a big thing. It's just a way of us staying in connection with each other and kind of, because I know it's easier to have class than to watch a video. So I'm just kind of like a little bit compensating you for, I know this is a pain in the butt, so thank you. But now, and I want to move on, but to like John's question, I just want to make this clear too, like, especially when I do have to miss class and I post a video instead, like often does happen on Wednesdays because of my other class that meets at the same time. When that happens, then I'm really giving you like the material of that day. Like, and I'm trying not to repeat myself. Like sometimes, like in the recent videos that you got, like there are things in there that I just don't have the time to say twice. So there could be intersection and sometimes there's emphasis, but sometimes there's things in there that I really like I don't have the time to say twice. So it's kind of like that important to me that you see them so that I know we're all on the same page. That's also why I'm giving you points for, okay? Like I'll answer any question here or reemphasize anything that anybody wants to go, but I'm also just going to assume that I've sort of said certain things because I said them in the video. So there is sometimes non-repetition to answer John's question. Okay. No, okay. So hopefully I answered Jessica's question, and yeah, hopefully I'm answering your questions on like we, she, and Jessica and Rachel and others. I'm not trying to make this a big, I'm just saying somewhere just in that portal where it says you could get up to 25 points. If you've noticed, just look back at the game assignments. If you've noticed anywhere where it says like up to 25 points and you've only gotten 8 or something, that's just because I'm just waiting for you to give me just one moment, just saying, yeah, watch the videos, dude. And I'll be like, good, here's the rest of the points. It's like, you don't have to prove anything. Yeah. Yeah, I mean, you could write a sentence, but so I think there were 4 videos last week, and I'm just really trying to emphasize that they would help you a lot if you watch them. And I think 3 of them went to one assignment portal and 1 went to another. Okay, does this make sense? Okay. Yeah, so does it make sense when I know some of these questions are now repeating. You don't have to testify, just tell me. And if you're lying, you're lying. I mean, okay, cool. Yeah, okay, cool. Oh, and for example, thank you, Rachel, for answering Zhao Wei's question. So that's points for closing for multiplayer co-op. And all of you still also, any of those old game assignments that have special, like, did you ever show video? Did you ever do multiplayer co-op? All of that, you still have time to hand in any of those before classes end. Even if they have a due date of like December 1st, which I didn't mean, I meant to change eventually, but I'm just saying anywhere you've done good stuff in this class, you have the opportunity to get amply rewarded for it. I just need you to take the extra minute to sort of tell me, and then I'll take the extra minute to give you the points. Okay, he's not going crazy. Okay, he's not going crazy. Right. Okay, I think you guys get it. Okay, cool. Okay, cool. Thank you. No, thank you guys. I appreciate it. Okay, and that was worthy. I'm glad we're moving on. Okay, so now the problem that I'm going to go over here, okay, again, is meant to if you can follow this, it'll make the problem in the final exam much easier. The problem in the final exam is an inclined plane that you look at more than one way. It's a little intimidating. It might be intimidating to look at now. Lab 5, I think, is intimidating. It is. And you might have already be done with it, but still might be like, what just happened there? The final exam is about an inclined plane. An inclined plane has a rough inclined plane, has lots of elements. It has roughness and it has inclination. We're trying to separate out all those elements so that you see them all and then can put them together on the final. So here we go. What we're going to analyze is this problem here, which is a box on a rough surface. The surface is not inclined here, but we're pulling the box at an angle as a way of seeing how angles work, okay? And to the left, I've given you the actual values, like the mass is 3 kilograms, let's say, in this example. Theta, the angle is like 30 degrees above the horizontal, let's say. Mu sub s, the static coefficient of friction is 0.7. The kinetic coefficient of friction is 0.4. That is an example right there of something I'm realizing when I talked a lot about friction and the coefficients. I believe it was last Wednesday on a video. Like I'm just saying, I don't think we directly talked about it, but I think it's in a video and I kind of need you. Okay, you get my point. But forgive me if it's a little confusing now to you. You might want to go back and see that. Anyway, the tension in the string pulling this block, I'm just asserting, is like 500 newtons. Okay, so now we turn the page. So what our ultimate question of this question is going to be, the ultimate thing that we would always be concerned about in any Newton's law problem is acceleration. All of this stuff that we're doing here is all geared towards calculating the acceleration of an object, because all the rest of our physics course, the whole assumption was that if you know the acceleration of an object, if you know the acceleration of an object at a given moment, then you could predict its velocity, and from its velocity, you can predict its displacement and thereby figure out where the object is going to be when. And that's the whole point of physics always, no matter what, like really at any level of physics, whether you're talking about planets or protons or baseballs or artillery, you always just want to know where is something when. And so the big bulk of our physics course so far has been like, if assuming we know the acceleration, realizing how much we can figure out from that. Now, at the end of the course, we're trying to backtrack and say, well, how do we get the acceleration in the first place? And the answer is forces, okay? So the ultimate question of this setup, like, will be, first of all, will this mass accelerate at all? Meaning, and this goes back to the video, but meaning, are we even pulling this object enough to overcome the static friction that is attempting to hold it in place? Any rough surfaces that come into contact with each other always exert friction. They first exert a friction called static friction that attempts to keep them in place. Once something overcomes the static friction, then the static friction seal is broken, and then the objects will start sliding along each other. And then once they're sliding, kinetic friction kicks into place. That's part of the video. It's always one or the other, never both at the same time. But so in order to get anything moving in the first place, we first, assuming there's any roughness at all, in order to get anything moving in the first place, we need first to overcome static friction, which really means if we just set up a situation like this one, just with facts, like I just gave you with these facts, before we even talk about how it's moving, we got to find out whether it's moving. So our first question here is going to be, is this mass even accelerating at all? Are we pulling it hard enough to get it moving? That's going to be our first, the ultimate thing we want to know. Then question 2 on the sheet here, assuming that we have pulled hard enough to overcome static friction and then we got it moving, assuming that it is accelerating, at what rate will it accelerate? That's really our ultimate goal. What will be the rate of acceleration? And notice it says there A sub X, like at what rate will this block accelerate horizontally along the plane of the floor, assuming we've gotten it to go at all. And if not, if the answer to question 1 is we didn't pull hard enough to get it going, then our question we have to ask is how hard must we pull in order to get it going? Okay, this is the ultimate thing we'd want to know for this situation. Kind of like the ultimate thing on the inclined plane is we'd want to know at what rate the object was accelerating up the plane or down the plane. It's always about acceleration ultimately, okay? But in order to get there, there's lots of sub questions and sub steps that we have to do. Always, like there's no way, even in my head, like I cannot just get the acceleration of this thing without going through a bunch of sub questions or sub steps first. Often on exams, our big questions are divided into these sub questions and sub steps. On your final exam, hopefully, mostly it's already broken down into sub questions. But whether it's broken down for you or not, in order to answer questions like this, we are going to have to do some things. So here we go. So sub questions needed for solution, like, and usually these are made explicit in the exam, but whether they're made explicit or not, you got to do them. The first thing we do, no matter what, is we draw a system schema. I'm just looking at the time. Okay. Now I'm going to pause for a second. Now, you know, this system schema, I know we have discussed a couple of times, like you guys and I, like in a lecture group. I know you've seen it in lab. For some of you, it's getting boring and old news. For some of you, it's old news, but still confusing. Let me say that system schema and then free body diagrams are the kind of thing that I used to vastly underestimate, honestly. First, as a student, for a long time, a good question. Okay, I'll answer that. Good question, John. Let me answer that in one. Well, okay, I'll answer. Yeah, it is string. Yeah. Okay. So okay, I'm glad you're paying attention. I'll just get to it. So here's the system scheme. Oh, good thought, Mark. Yeah, it's actually what she's saying. God, you guys are so good. This discussion is so much more productive than anything I could say. Okay, CE, I mean center of Earth. So here's what I have in this diagram, and I'll explain. All right, so the mass is the object of interest, dotted circle, it's our focus. And then what I'm doing, as I do in every single system schema, first, I always put a circle indicating the center of Earth. CE stands for center of Earth, or you could say PE, like planet Earth. Yeah, okay. Oh, okay. Or celestial Earth. That is a good name. First of all, it's cool sounding, but also that's good. You could say CE for celestial Earth or PE for planet Earth, or you can even say, in some diagrams will say, if you look up on the web, you could say EE, meaning entire Earth. What we're trying to designate with that one circle that goes into every single system schema without fail. And it's always the first thing I draw in any system schema. And I don't care where I draw it, but I draw it in the system schema. I'm trying to indicate that there's always this planet Earth, the center of which somehow is always pulling on anything and everything that I'm studying. It's always there, so I always put it there. But also somehow it has this ability to pull on things without touching. Like if I didn't remind myself, if I didn't realize it was always there, I might forget it, because everything else, and this is important, everything else I'm going to put into that diagram, and everything else that I'm going to focus on, like literally everything else besides planet Earth, is going to be a touch. I am not going to put anything in that diagram that isn't physically touching my mass, and I'm not going to leave out anything that's physically touching my mass. The exception to the touch is center of Earth, or planet Earth, or celestial Earth, or entire Earth. So And I say all those things also to distinguish. The reason I also don't just write earth is because then you might think I mean like dirt or ground or something. And that's not what I mean, because something could be sitting on the ground and then the ground is pushing on the thing. That would be a different other force. I'm talking about the actual center of our planet, gravitationally pulling on our object. It's always there. So I draw a circle indicating that, and then I draw a line from it to our mass. That line that's connecting center of Earth to our mass, that line is supposed to represent a force, right? And this is the ultimate point, is we're trying to identify carefully and count up forces that are acting on our mass. That is our goal here. And I know this seems like a dumb sketch and it seems like a dumb step that you could just skip, but honestly, it's the key step because it's so dumb that it does the work for you. This is the step where we figure out exactly what are and what are not the forces that we have to count in the math. This is the step that sets up the math. And if we really all sit back and think about it, it's always the steps that set up the math that really are the challenging ones. Most of us do, let's be honest, most of us often will say that I'm going to look in the chat in 1 second. Let me just say this. I mean, I see there's something in the chat, but the reason for this, like the dumber these sketches look, both this sketch and then the free body, I'm going to spend most of today doing these diagrams again. And I'm sure I'm driving some of you crazy thinking like, it's always about the diagrams. Can't you get to the math? Honestly, if you really think about it, for most of us, once the math is rolling, most of us at one time or another in a science class or a physics class have said, I know how to do this. I get what he's talking about when he's talking, but I don't know how to do it on my own, or I know how to do it on my own once it's going, but I don't ever know how to sit down and start these problems. I'm trying to tell you all that the real way to start these problems is with the diagrams. The diagrams do the heavy lifting for you, and they make the math actually possible. The purpose of these diagrams is to figure out exactly what are and what are not the forces, and ultimately in what direction are they acting, so that we can plug the proper F's into the left side of F net equals MA. Our real goal here is to figure out what F's are going to be added up to be plugged into F net equals MA so that we can solve for A. It's all about solving for A. The hard part is getting the F's to solve for A. We get them from the diagrams. That's why we're doing this. Let me just look in the chat. Hold on. Sorry. The chat looks good. Let me just see. Okay, it's CE, center of Earth. So yeah, so CE means center of Earth. I like Mark's name too. Mark's name is Mark Lewis. Oh, Mark's name, yes. No. And yes, thank you. That totally counts as multiplayer co-op, by the way. Okay, for SS. Now, good question, John Ford. Oh, great question. Really good question. Okay. Oh, and great answer, Maisha. Wait, so I'm going to respond to this, but I'm going to look to the rest of Siva. But John Ford's question for SS, do you only focus on forces acting on the system or also forces exerted by the system? It's a really important question. And I really do like Maisha's answer of it's about what's interacting. I'm going to expand on that in a moment, but this is a very important question because John Ford's question and Maisha's answer are exactly what distinguish the SS, which we're building right now, from the FBD, which we build from it. So it's a very important distinction. I'm going to give my response in a second. Let me just see the other responses. Yeah. So what Maisha's saying is right. SS is all about the objects and the forces between them. Well said, yes. And then Starnisha is right, acting on the system, touching at, yes, anything that's acting on the system by touching plus planet Earth is what goes into SS. You guys are totally filling me with joy. So I love John's question. I'm still going to add my response to it, but I love Maisha's answer. I love Starnisha's answer. John. Yeah. Oh, great. Oh my God. Awesome. Yeah, no, seriously, John, Starnisha, Maisha, awesome. And anybody else who's following this, first of all, totally multiplayer co-op. Oh, I need to make up totally multiplayer co-op, totally closing the conversation, totally correct. Oh, also, you guys can also apply for points for right or wrong thing, and you're all right. Now, here's why it's particularly awesome for everybody. Absolutely right. If these lines in this picture, these lines are just lines, they're not arrows. And that's very on purpose. We're using this picture to generate lines from which in the next picture, we will generate arrows. Now, in this picture, they are not arrows. Totally right to bring this up. If they were arrows in this picture, I completely agree with John Ford and Maisha and Starnisha that I should write a poem that, no, I shouldn't. I totally agree that if these lines did have arrowheads, they would necessarily all be double like they'd be heads on both sides. That is absolutely right. The point of these lines is that they are showing the interactions. They're showing the reciprocal symmetric interactions. Like, so for example, that line between CE and M is literally trying to say Earth is pulling M, therefore M is pulling back on Earth, which is totally true. That's Newton's third law. Or then like the string. Okay. They are literally trying to show the interactions. And the reason we're doing this diagram first is what we're really trying to do in this diagram is get a firm, confident knowledge of exactly the number of interactions that are going to go into our free body diagram. Right here, our whole goal is to identify exactly what is a force and what isn't. In other words, we're trying to generate a list of the actual forces. And this is the part that if we didn't have these diagrams, this is where people like make a lot of mistakes and will screw it. And this is the part that starts the math off. But so the rule for making this diagram is we care only about, we put in Earth first, and then we just put in any and every object that is actually touching our mass. And that's what the string is an object that is touching our mass. So we draw a circle representing the string. Like you might not before this have ever thought of a string as a thing. A string is a thing and it's touching our mass. So we draw a line between the string and our mass. By the way, how is the string doing that? How is the string pulling our mass? Well, because someone's pulling the string, but no, presumably. And how is that person pulling the string? Well, either because they're doing some biological chemical thing inside their body, or because they're pushing their foot against the floor and leveraging themselves, or both. But notice, I don't care about any of that. I very deliberately don't care about the person that's holding the string or the chemistry that's motivating the person to hold the string, and the reason I don't care, I'm not saying it's not true, but the reason I don't care is because once I start caring about that person, then I'm going to care about their cornflakes that they ate this morning, or I'm going to start caring about the floor that they're standing on. And once I care about the floor that they're standing on, then I'm going to care about the foundation of the building. And I won't know where to stop. And the honest thing is the reason people have a hard time starting these problems and doing these problems is because with smart people like you guys and good students like you guys, and I'm not kidding, there's a tendency to overthink. This whole exercise is meant to cut off our thinking and say, all we ever have to care about is anything immediately, directly touching the object. Anything immediately, directly touching the object will exert a force on it, plus planet Earth, because planet Earth is special. And finally, we're saying, and then I'll look in the chat and again and go on. We're saying for every object that touches our mass, there is one force. It's the one touch, one line rule. And the string is the one really following that rule here. It's an object, it's touching our mass. So we draw one line indicating that that object is pulling our mass. It is following the rule. Now there's two exceptions to the rule, always exactly two. They're just weird, but they're always there. So they're like a little weird and they look like rules unto themselves. One is that center of Earth always does pull our object without a touch. So we put it in first so we don't even get confused. So there's a line there with no touch. And I'm going to look in the chat and I'm going to move on in a second. I'm looking at the time. Then notice the table. The table is the other thing touching our object, right? And again, the whole algorithm is just put in Earth and then just put in every object and only every object that's directly touching ours. So we put the table in because the table's touching ours, but the table is a surface that is pushing against the surface of our object. No, as opposed to the string. The string was a pull. It was a line that's pulling on our object. The table is a surface that's pushing. And what I tried to explain in at least one video and in at least one class is whenever surfaces pushing, whenever rough, realistic surfaces push against each other, there's this funny thing that happens where by pushing like this, they also automatically push like this. Because rough surfaces are rough, they interlock with each other. So whenever there's a squeeze, there's also a rub. And that whole phenomenon is called the normal and the frictional components together of pushing. This is the normal component of pushing, normal meaning perpendicular to the plane of contact. And this is parallel to the plane of contact. It's called friction. They are just the two components that always accompany each other, that are always there if surfaces push against each other. So the fact that the table is a surface and it's pushing on our object, I immediately put in two lines because that will be the case. So now this system schema, I'm going to pause for a second. I'm going to look in the chat, but I'm saying, what was there's nothing else going on in the system schema. There's no arrowheads like you guys are pointing out. Also, I notice I just put the earth in a random place. I put the string in a random place. I put the table in a random place. I'm not at all concerned with direction or even names of forces or any detail or numbers. All this is meant to do is force me to generate a correct and complete list of what actual forces are acting on the mass. According to this picture, the earth is pulling on the mass, the string is pulling on the mass, and the table is pushing on a mass in two different ways with two different forces. Hence, and I'm going to look in the chat right now, but the real purpose of this diagram is, if I believe it, if I just made this dumb sketch according to this dumb rule of do earth plus all the touches, then what I now know is when I go to do my free body diagram, which comes next, and which is really the point, or the next point, when I go to do my free body diagram, where I start putting in arrows and I start caring about direction and stuff, I'm going to know that there had better be exactly 4 arrows in my free body diagram. That is really the purpose of this, is to force me, to keep me on the right road and make sure that when I go to do the free body diagram, there will be exactly 4 arrows, because there's 4 lines here. And I'm going to do that, but let me pause and look in the chat. Wait, so, oh, wait, okay. In fact, I'm even going to, I'll flip the page so you can, okay, yeah. Well, actually, let me look at the, sorry. Let me look at the chat for a second. Okay. Well, actually, yeah, no, here, you can look at this while I look at the chat. You're welcome, no problem, John. Oh, so to John's question, we don't include the hand, we don't include, because the hand, presuming that there was a string pulling on the box, if there was a hand pulling on the string, we don't include that, because our object of focus was the mass. So we're only putting in objects that directly touch the mass. I mean, it's a great question, John, but it's kind of my point of the whole thing is we're trying to force ourselves to cut off analysis at a certain level. We are just putting in immediate direct influences, which means immediate direct contact. Right. So in the system schema was just a line representing the tension from the string. And you'll notice that now, I mean, I'm going to talk about this now, but now from all that, I generated this free body diagram here at the bottom of the page. I'm going to explain it. I'm just looking at the chat first, but here now we start caring about directions and stuff. That string line from the system schema became an upward rightward pointing arrow labeled T in this diagram, the tension in the string. And I'm going to explain that. So let me just look in the chat if the hand isn't right. Right. Oh, good, Maisha. Right. Good. It starts with caring. Okay, that's hilarious, John. Yes, it starts with caring what they. Right. Well said, John. Do we always have to include another force friction? Yeah, I think so. Maisha's question and John's answer, where I think Maisha asked, do we always have to include another force paired with friction? If I understand that question correctly, then I do agree with John's answer. Like if you ultimately have a free body diagram that has friction in it and there's no normal force, something's wrong. There's no way to have friction without a normal force. Normal and friction are the 2 components of one overall phenomenon. The overall phenomenon is surfaces pushing against each other. So in order to get this in order to have this sliding resistance, it's because 2 things are squeezing against each other. In fact, so you can't have F without N. And in fact, that was the purpose of, I think, maybe the very last video that I posted, is actually showing you that the friction force equals the coefficient of roughness times the normal force. The harder you push 2 things together, and the rougher they are, the more they will resist each other in the rubbing, sliding direction. So friction really emerges as a result of 2 contributing factors: roughness, which is designated by the number mu, and squeezing, which is designated by the normal force. So I think this is Maisha's question and John's answer. If you see friction in the diagram, there better be normal. Now, conversely, if you see normal, there had almost definitely better be friction, unless you've been told that the objects are super unrough. If mu is 0, if it's like an air hockey surface, cushion of air, or like a perfectly smooth table. If you're being asked to assume that the surfaces are approximately perfectly smooth, then they might squeeze against each other, but have a mu of 0 and therefore not rub against each other. So that can happen, but friction equals mu times the normal. If there is a normal, then there's friction. And if there's friction, there's a normal, unless mu happens to be equal to 0. Okay, so, oh, wait, great question. No, I mean, not to be rude, and you could put this in for like the for right or wrong, but wrong thing. Tension is a real thing, but tension is not ever what's going to create friction. You can have friction without tension, and you can have tension without friction. It's the normal that goes hand in hand with friction, because normal is about things pushing against each other, specifically surfaces pushing against each other. Tension is our word for a line pulling on something, like a string or a rope or a rubber band. So these are great questions. I might be leaving people high and dry, but obviously I want to explain this diagram that I've put here, but this, just as long as I'm still looking at the chat, this diagram that's now on this page is the free body diagram of our situation. It's built from the system schema. Notice certain details are being left out, but certain new details are being put in, but it's all one situation. Let me just look. Yeah, friction is a side, good, Starnisha, yes. Friction is a side effect of normal force. That's right. That's well said. That's absolute. And then Mark, is the normal force value equivalent to that?
You answered the question already. Thank you.
Okay, all right, thank you. Wow, you totally just got points for, okay, great, thank you. Appreciate it. Okay, all right. Oh, yeah. Oh, and good, John and Starnisha, maybe I really should read the thing before but yeah. Like normal, like every single force in the world is either a push or a pull. Every single force in the world is either a push or a pull. And by push, by the way, I mean like away from, and pull, I mean toward, like whoever's doing the pushing or pulling. And I don't mean that as a joke, like that can be confusing, but by push, I mean away from, and by pull, I mean toward. Normal is always a push. Tension is always a pull. Gravitation is always a pull. Friction is always a push. And it's just like, that's just the categories of it. So I don't know if that helps or not, but by tension, we always mean like a string pulling on something. And by normal, we mean a surface jamming against something. Okay. So I think, okay. I'm looking at the chat is great. I think, especially because of the way Mark just, I think in a second, I'm just going to skim through this chat and then I'm going to get back to, I think a lot of this will be answered or is already answered if I start explicitly talking about this diagram. Yeah, ice has super low friction. Right, like ice has a mu of like 0.1, let's say. An air hockey, an air cushion has like 0.000. Ice would be like 0.1. Glass would be like 0.2. Then like wax polished skis or something like 0.25 or 0.3. Then, then wood, really polished wood, 0.4. And then what am I? Velcro, very bad, like 0.8, or say rubber, like 0.9. It's like that. Okay. Yeah, we used to do that. Honestly, I used to take classes to Chelsea Piers and stuff. I mean, we also used to go to Great Adventure, but I mean, hi COVID. Well, also hi me getting old and lazy. But okay. Okay. So this diagram now. Look, let's see what I did in this diagram. This is the pure free body diagram of our situation. I'm looking at the time. Oh, okay. What I literally did was I took each line from the system schema and put it into here. In the system schema, we named objects as a way of forcing ourselves to identify forces. Like we were like, oh, there's a string touching our object. Oh, then the string must be pulling via this thing we call tension. Oh, there's an earth. Oh, it's pulling on our object via gravity. Oh, there's a table. Like we just named the objects to make sure that we weren't just like making up forces. Like, and yeah, oh, that's hilarious. Oh my God. Don't get me started on that. So in the system schema, we're naming the objects because we're really trying to remind ourselves at all times, you cannot just make up a force just because you want to, especially forces that have names like normal, very deceptive, very dangerous name. It really makes people think that, like, honestly, a lot of people, if you're not careful about these diagrams, a lot of people will take a situation like free fall or something and start drawing arrows, and then they'll put in a normal force in something free falling because they're like, oh, well, since there's gravity, there must normally be a normal force there to counteract gravity. Or something. No. forces, like, no, if something in free fall, there's no normal force at all. Or if I were just pulling up a fish out of water, there might be tension from the rope, but there's no normal force there at all. Normal doesn't mean it's always there. And there's no force that comes in just to rescue us. We don't put forces into diagrams just because we want them to be there. What we're trying to say is that a force acting on me can only come from some other object in the world interacting with me. So in the system schema, we name those objects, and we name the mutual interactions that are happening between those objects and us, or our mass, our object of interest. But now we get to the free body diagram, and now we shift our focus. Now we're like, all right, we've done our work. We know there's going to be 4 forces acting on our mass. Our ultimate goal is to see how our mass accelerates. So we are interested in the forces happening to the mass. So now, and this again goes back to the whole Star-Nisha, Maisha, John discussion of earlier on. Now we focus down our attention and we say, for example, we say with the Earth pulling down on our mass, we put a downward arrow and say there's a downward force on our mass, sometimes known as gravitation, sometimes known as weight, and sometimes mathematically, or in fact, always mathematically designated as mg. Again, please watch the video to understand where this whole mg thing came from. But in short, it's not m, it's not just the mass, it's not our object, it's the pull of gravity pulling on it. And lowercase g is the letter that we've used all class, all semester to designate the acceleration rate of something in free fall, right? Lowercase g just means like 9.8 meters per second squared. And m just means the number of kilograms that this thing is. We're saying multiply the two together and you have the value of the force, like mass times acceleration equals force exerted by the Earth pulling down on this object. All objects have a weight. All objects are pulled down toward Earth by a certain number of newtons. That weight of every object is not the same as its mass, right? It's the actual force being exerted by Earth, and that weight is designated m times g. If my mass is 3 kilograms, then my weight is approximately 30 newtons, like, or 29.6 newtons. Where did I get that from? I took 3 kilograms and I multiplied it by 9.8 meters per second squared, or I rounded up to 10 meters per second squared. And I say, if my mass is 3 kilograms, then my weight is like 30 newtons. Okay. What I'm trying to say though is notice that downward arrow for mg, that by the way, goes into every single free body diagram, just like the CE goes into every single system schema. Every object has weight. Every object is being pulled toward Earth. So I put a downward arrow. Now it is true that if the mass is being pulled toward Earth, then the mass is also pulling up on Earth. That was indicated in the system schema. That is demanded by Newton's third law, but I don't care anymore. Now that I'm into the free body diagram and I'm trying to analyze what's happening to the mass, I don't care anymore what the mass is doing back to other objects. What the mass is doing back to other objects is not in this diagram. It would be in diagrams of them, right? Like the fact that the mass is pulling up on the Earth, true story. But that would be an upward arrow in a picture of Earth. Let me go on and say, for example, the table is pushing up on the mass. The table is pushing up on the mass with a force known as the normal force. Like, again, notice I said table in the other diagram because I was just trying to figure out what objects were interacting with this darn thing. Now that I know, I'm literally putting the names of the forces here. Like now I'm looking at the forces themselves, now that I'm convinced that I identify them correctly. So I've got this table that's pushing up on the mass. It's pushing up with this force called a normal force, like the capital N there. Now notice, and I will look in the chat, I'm just looking at the time. I'm looking at, hold on, I assume the chat. Funny, okay. Notice a couple, so right now I'm talking about the N, the upward arrow of N. Now it is opposite in direction to the downward force of gravity, but notice, so now I'm drawing vectors, right? Now I'm trying to draw a vector to represent each force because I'm trying to set up the math, like that's what this is about. And each vector is supposed to have approximate reasonable magnitude and approximate reasonable direction. Now, there's no numbers here, so I'm not being exact, but I'm trying to give myself a sense of how comparatively big or small these different forces are as measured in newtons. And I'm definitely really focused on in what direction they're pushing or pulling. So that normal force is pushing up. It's the normal force from the table. If the whole table were slanted, as it is in the lab in the inclined plane thing, then that normal force would be tilted, right? Why is it? Great. Okay. So I just got a question in the direct chat. I won't say the person's name because it's direct chat, but it's exactly the question I was about to address. So I'm very glad someone's with me. So in the direct chat, someone who is very smart, but shall remain nameless, said, why isn't the normal arrow the same magnitude as mg? Okay, that's totally what I'm getting at right now. Great question. No, yeah, no, good mind reading. No, I'm psyched. And you should definitely submit this question for points here, because it's, and I'm glad someone's raising this because this is on a lot of people's minds often. And in some people's, they don't even realize it's on their mind. Wait, hold on. I'm about to answer, but let me just. Yeah. Wait. Oh, okay. So quick digression. Just remember the normal. So so I'm going to answer these questions just slightly out of order. The normal that. Yeah. Good. I love this class, and it's funny. Yeah. So the normal force just literally means the component of push from the plane acting on our mass that is perpendicular to the plane of contact between them. So that arrow that, and I still haven't answered the magnitude question yet, but I'm about to. But that normal up. Okay, that's funny. And yeah, please. And good luck supporting a family too. I mean, on the sat. Okay, anyway, the plane is pushing up on our mass. The plane of contact is horizontal, so the push up is vertical. And that's all that normal is indicating. It's indicating that I've got a plane. Wow. That plane is pushing against the mass. If, just to go out of order with these questions for a minute, if the plane started tilting, if it became an inclined plane, as in lab, I can't even do the mirror image thing here, as in lab 5, if the plane tilted, then the plane would be pushing at an angle. So the normal force that normal arrow would be at an angle, as it is in lab 5, by the way, and as it is in the final exam document that we're eventually relating this back to. Like in an inclined plane, that normal would be tilted. But now to answer direct chat person's question, mg is still mg. Mg is happening because of the Earth. What I want to say here is these two forces in this case are opposite direction. So they might look like they're a Newton's third law thing. It might look like it's like action and reaction. So it might look like the normal force has to be equal to the gravity. It's very reasonable to get in the habit. It's very common to get in this habit of thinking that the normal force has to be equal and opposite to gravity. What I want to tell all of you, like definitely direct chat person, but all of you is, this is not Newton's third law. This is not action reaction. It looks like it, but it's not. Action reaction is never seen in one diagram at the same time. That is, put it again, like the Earth pulls down on the mass. Okay, that's action. Therefore, the mass pulls up on the Earth. That reaction is true, but would go in a picture, would be drawn as an arrow in a diagram of the Earth. Similarly, the plane pushes up on the block. The reaction to that, okay, hold on. Almost really good. New direct chat person, almost really good. Hang on one second. This plane pushes up on the block, not as a reaction to Earth, but it just does because the block is on the plane. The reaction to that would be that the block pushes down on the plane. Like that's true, and that's equal and opposite, but that would go in a diagram of the plane. And we're not here trying to analyze the acceleration of the plane. We're here just analyzing the block. So a couple things. So one thing I'm saying is, there's no law that says if Earth pulls down on block, plane must push up on block. That is not a law. By the way, this is why I tell you to write down Newton's third law like the way I told you to write it down. If A pushes B, then B pushes back on A in exactly the same magnitude, but in opposite direction. What I want to emphasize, and people get this wrong in life all the time, Newton's third law is about two different objects interacting with each other. It is not about one object. There's no law that says just because something's pulled down, it must be pushed up. If there were such a law, if there were a law that says anytime there was gravity pulling down, there must be a normal force pushing up with the same magnitude, then nothing would ever free fall and nothing would ever accelerate. What I'm really long-windedly trying to say here, and then I'm going to get the other direct chat thing, is that normal force is just doing whatever it's doing. It might or might, if this were a really simple situation where something were just sitting on a plane, then probably the normal force probably would equal gravity. It probably would if the thing were just sitting there, because the two forces would have to cancel each other out to produce an acceleration of 0, i.e. Newton's second law. But the real reason that I believe that that normal force is small. Now, so here's finally my answer to the very good question. And then there was a follow-up from a different direct chat person. The real reason that I am conjecturing in advance that that normal arrow is going to be smaller than the mg arrow is because there's also tension. So someone put in the direct chat, is it because the object is able to slide horizontally? That's like a really good thought. That's like almost the right answer, but honest, or maybe indirectly it is, but really okay, cool. What I'm really, awesome. Thank you very much, direct chat. I totally appreciate it. I'm going to just finish this point to everybody, but it was a great question. Really, the point is that there's a string pulling to the right and up on the block. When I get to the point of resolving that T into components, when we look at that T and realize that by pushing up and to the right, it really is pushing up, by realizing that it's pulling up and to the right, we'll realize that it really is pulling up and to the right, both at the same time, but independently. That means that that string is pulling up somewhat. So together, the string and the normal force together must be supporting the weight of the object. If the object is really not accelerating up or down, if it's really, so I guess this is also a way of answering the other direct chat person's question. If this object is accelerating only horizontally, if it's not accelerating vertically up or down, that means all the vertical forces must be balanced. That means that T, a component of T, is doing some of the vertical pulling and therefore helping out the normal force. The normal force doesn't have to do as much as it would if the T weren't there. In short, if the T weren't there, I probably would believe that the normal would be, and nothing else were going on, then the normal probably would be equal to the mg. But all of this is to say there's no law that says n has to equal mg. There's a law that says n has to do what n does. There's a law that says F net equals ma. All the forces together must produce the acceleration. I think what we're going to find is that n up plus the upward component of tension, together they will support the downward weight of the object. So that was a great question, though. And that, so I'm going to look in the chat again in a second, but I really appreciate the OOKs and everything that I got in the chat. Let me say what is drawn here, and we're not done yet. I mean, for round one, we have 10 minutes left, but also we're still making diagrams here. And believe me, again, I know that to many of you, like sitting around drawing diagrams doesn't feel like what you thought physics was supposed to be. I'm sure many of you would rather just be doing the math. I get that. But honestly, that's really secretly because the math is like not the hard part. This looks like the dumb kindergarten part, but it's not. This is the part that does the heavy lifting for us. And the dumber it feels, the more effective it is, because it means we can turn off our brain and just follow these diagram rules. And next thing you know, the math is ready to go. Okay, so what this diagram has been, what this diagram is the pure free body diagram. It is stage 2 of setting up the math. We took our system schema, and now we took each line from the system schema and drew it as a force that is actually occurring. Like we're drawing the arrow to represent what is actually happening to our mass of interest. It's being pulled up and to the right by tension. It's being pushed up by the normal force of the plane. It's being pulled down by planet Earth, and it's being pushed to the left by some form of friction. That's our pure free body diagram. Before I look in the chat, before I go on, I want to say we do all this so that we can start plugging in arrows and values into the left side of F net equals ma, the left side, right? But we've got one more step we've got to do, even if I run out of time. And that is, I've got to resolve these vectors so that everything I see is on a y-axis and or an x-axis. Like F net equals ma is a vector equation. What it really means, what F net equals ma really means is the sum of all of the forces on the x-axis, including minus signs, will produce the acceleration along the x-axis. And yet, simultaneously, while independently, all the forces acting on the y-axis, added all up, taking into account minus signs, will produce the acceleration along the y-axis and also on the z-axis. F net equals ma is really a vector equation, which really means it's a set of simultaneous equations, one for each axis. The problem here is we don't have clear axes going on. We've got vectors, we've got arrows going in all kinds of directions. We need to clean this up so that we only have arrows along a y-axis and an x-axis. That's what we're going to do next in the component diagram. We're going to turn the page. I'm going to look in the chat. Hold on. Yeah, so look, so if you're already caught up, please look at the next page. I'm just looking at the chat. Really good question about springs. Really good question about springs. I'm not going to get into a whole thing right now. In fact, a huge part of physics 204, honestly, is all about springs, to tell you the truth, the beginning of it. But I understand why John's bringing it up, because the normal force secretly is kind of acting like a spring. He's totally right. Like the heavier things are, the more you push down on a surface, the more it seems to be able to push up, much like a spring. And he's right, because electromagnetically, microscopically, electrons that are on the surface of all objects act like little springs, as in the closer they get to each other, the more they resist and repel each other and want to bounce away. Microscopically, there's a lot of springy action going on. John Ford's not crazy to bring that up. But that's all I'm going to say on the moment. The actual study of springs, we're going to wait for physics 204. Yeah, like there are more complicated, good point, Lizzie. Right. I mean, there are more mechanics involved in springs, which we'll get to later. Okay. Yes, direct chat. Sorry. And good. Look, me too, Maish. I prefer the diagrams too. Hold on. So I'm just catching up to the chat. 1 second. All right. So now, and I know we have like 6 minutes left. Now our goal is to break up vectors so that all we see are arrows along X, Y, and Z axis. Again, this all goes back to Galileo. That Galileo says the laws of physics are the same in all reference frames, in all coordinate systems, even as simple as the coordinate system known as the x-axis or the coordinate system known as the y-axis. Physics just happens independently according to the same rules along each axis. So we want to divide this picture into axes and then be able to do F net equals ma along each axis. Now, the beauty of Galileo is that whatever we call our axes, this will work. But in order to actually divide vectors into axes, we actually have to consciously choose our axes. And honestly, this is going to sound a little bit abstract maybe, but this is really what's going on in that final exam document once you feel like looking at it and stuff. Again, it's all about an inclined plane. But when you start looking at that final exam document, you'll notice that we actually ask you a bunch of questions about the inclined plane sort of twice, 2 different ways. We ask you to analyze the inclined plane with a set of axes like this and get a bunch of answers. And then we ask you to analyze the inclined plane with a tilted set of axes. We ask you to do everything with 2 different set of axes so that you can see that on the one hand, you can get correct answers no matter what axes you use. But on the other hand, you'll see that certain set of axes are a lot more convenient and easy to work with than others. And you certainly won't get correct answers if you flip-flop and forth between axes in the middle of a solution. So the whole thing of Galileo, again here, and it's all about Galileo, is that freedom gives us the choice. We can choose from what perspective we're doing physics, but because all the perspectives will work out in the end to the same correct answers. But physics says, but you've got to consciously make that choice. Because if you don't know what choice you've made and you flop around between choices, you won't get consistent answers. And physics also says you got to consciously make that choice because some choices will be a lot more convenient than others. So what I'm literally saying is we're going to have to choose. In other words, we're going to divide up vectors into components that lie along an X and a Y axis. In order to do that, we have to consciously decide, are we doing our conventional thing of calling this the x-axis, like a line parallel to the ground, the x-axis, and calling a line parallel to gravity, the y-axis? Is that what we mean by x and y? And most of us in the room right now would probably say, well, yeah, what else would you do? Like, why wouldn't you do that? Like, duh, yeah, do that. Okay, and guess what? To those of you, I say, yes, that actually is what we're going to do here. But another choice might be to line up the axis, to rotate our axes so that the x-axis is like lined up with tension, for example. Now, that's not going to be a great choice here. But you may or may not have noticed, that that is what happens in the inclined plane in your lab. And frankly, it may have confused a number of people. And some people might have eventually worked it out, and others might have just skipped over the confusion and just accepted it as black magic. But you'll notice that in your lab, and I got to say this, okay, we're running, in the lab, you actually tilt your axes to line up the x-axis with the inclined plane. And it's confusing at first. And then you end up breaking up gravity That can be very weird and confusing at first. The ultimate point of our final exam is in a way to show you why we do that. But what I'm saying here is that's a choice. It's not that we do that all the time. How do we know what axes to use? How do we know when to tilt them and when not? The answer, and I know we're just about out of time, but the answer is here's the strategy. The one strategy that will work and be helpful at all times, including the lab, like the strategy is you line up your x-axis with the expected direction of acceleration. And I know I'm running out of time, so I'm going to say this sort of quickly here, but like in this case, we expect the block to accelerate horizontally. So yeah, I'm going to say that my x-axis is horizontal. In the lab, in the inclined plane, you expect the object to slide along the plane. So we actually tilt our axis and we line up the x-axis with that tilt. It's two different things. It's ultimately the same strategy, but it ends up making for different components. Why do we do this? One quick answer, because I know I'm running out of time. One quick answer is if we line up the x-axis with acceleration, then we can really solve F net equals ma. If we don't do that, we're going to get acceleration along more than one axis, and we're going to have to split up acceleration into sines and cosines. That means even before we put in forces, we'll already have sines and cosines on the right side of the law. We're trying to minimize our efforts here on our sines and cosines as best we can. So we always line up our axis with the expected result of, direction of acceleration. Therefore, and I know we're about to run out of time in this case, but we have one more page and we're done. And obviously, if we have to go. So I'm saying here in this case, we're going to make the x-axis parallel with the plane with the direction of expected acceleration. And therefore, we look at all the arrows are then in our coordinate system, like normal, gravity, and friction are all fine, but tension is the one that's off kilter. It's the one that's neither along the X nor along the Y. So we zoom in on tension and we use trigonometry, SOHCAHTOA, and we get its two components. We say tension is really pulling somewhat to the right and somewhat up. So we divide it and only into components. Why do we divide it? Because it's the one that's not lined up along the X or Y axis. And then we substitute, and this is our last stage, and then goodbye. What we do is now say from here on in, there's no more tension. There's a X piece of tension and there's a Y piece of tension. We substitute those pieces back into our diagram. This is our final page. This is it. In other words, we had a system schema that had 4 lines. Therefore, we made a pure free body diagram that had 4 arrows. Then we chose a coordinate system. We looked at the arrows in our pure free body diagram, and any arrow that was off axis, we divided into 2 components. So the one arrow of tension became 2 arrows, T sine theta up, T cosine theta up. It didn't, and nothing else got changed. So now we have a diagram that has 5 arrows in it, but all of them are parallel and perpendicular to each other. Now we can use this diagram. Now we can literally do F net equals MA along the x-axis, and we could separately do F net equals MA along the y-axis, and everything is clean and ready to go for the math, and that's where we end today. But thank you for paying so much attention and totally clearly following me. I will miss you. I'll see you in 2 days. Oh, no. No, you guys are good. Oh, great. Oh, great. Thank you, guys. No, thank you very much. But all of you, both of you. Wait. No, you guys rock. Thank you very much. Yes, have a wonderful day, Needed. Great job, people. Seriously. I think you did great. Yes, have a great day. Yes, good night. Good job. Hold on, I'm going to turn.